Have you ever wondered how engineers detect invisible cracks in aircraft wings, engine parts, or critical welds that could lead to catastrophic failures? What if I told you there's a simple yet incredibly effective method that uses colorful liquid dyes to reveal hidden defects that are completely invisible to the naked eye? Welcome back to the channel. Today, we are diving deep into one of the oldest yet most widely used non-destructive testing methods in the world. Dye penetration testing, also known as liquid penetrant testing or DPT. Whether you're an engineering student, a quality control professional, or just curious about how industries ensure safety, this video will give you a complete understanding of this fascinating testing method. So let's get started. Dye penetrant testing is a non-destructive testing method that uses liquid applied to surfaces to identify surface breaking defects in non-porous materials. But what does that actually mean? Let me break it down for you. DPT is one of the oldest and simplest NDT methods, with its earliest versions using kerosene and oil mixtures dating back to the 19th century. The basic principle is beautifully simple. If you have a crack on a surface, and you apply a thin, colored liquid to it, that liquid will seep into the crack through a phenomenon called capillary action. The method is based upon capillary action, where low surface tension fluid penetrates into clean and dry surface breaking discontinuities. Think of it like this. Imagine you spill water on a table, and it immediately flows into any tiny scratches or cracks in the surface. That's essentially what's happening here, but with specially formulated dyes that make those defects visible. The method is used to uncover surface defects in a wide range of materials, and it plays a crucial role in ensuring product quality and structural integrity across numerous industries. The beauty of this method is its versatility. It works on metals, plastics, ceramics, and even composites, making it one of the most universal testing methods available. Now you might be asking, why is this method so important? Why can't we just look at parts with our eyes or use a magnifying glass? The answer is simple. Many cracks and defects are microscopic. They're so tiny that they're completely invisible to the human eye, yet they're large enough to cause catastrophic failures under stress. DPT is used in production processes to verify that materials and components meet specified quality standards during manufacturing, detecting surface breaking defects such as cracks, pores, and inclusions to ensure the integrity of the final product. Imagine a crack in an aircraft landing gear that's only a fraction of a millimeter wide. Under normal conditions, you'd never see it. But when that aircraft lands with thousands of pounds of force, that tiny crack could propagate and cause a complete structural failure. Dye penetrant testing is crucial for inspecting welds to detect surface breaking flaws such as cracks, lack of fusion, and porosity. Ensuring weld integrity is vital for the structural safety of welded joints. From aerospace to automotive, from power plants to pipelines, DPT is the guardian that stands between safe operations and potential disasters. Before we get into the actual testing process, let's talk about the two main types of penetrants used in this method. Type 1. Visible dye penetrants. The most common color combination is red dye penetrant with white developer, which ensures that damaged areas can be easily detected under good lighting conditions. These are typically bright red liquids that you can see with your naked eye under normal lighting conditions. They're the most economical option and perfect for routine inspections. Type 2. Fluorescent penetrants. Fluorescent penetrants contain dyes that fluoresce when excited by ultraviolet radiation, also known as black light. When you shine a UV light on them in a darkened environment, they glow with brilliant yellow-green color. This material is more sensitive to defects since the excited dyes emit light that contrasts strongly against the dark background. Fluorescent penetrants are used for critical applications where you need to detect the smallest possible defects, such as turbine blades or aerospace components. They're more expensive but offer superior sensitivity. There's also a third option called dual-purpose penetrants that work under both normal and UV light, giving inspectors flexibility depending on the testing environment. Now let's get into the heart of the matter. How is dye penetrant testing actually performed? The process involves 6 critical steps, and each one must be executed properly for the test to be accurate. Miss one step or do it incorrectly, and you could either miss a critical defect or get false indications. The 6 steps are: surface cleaning and preparation, penetrant application, dwell time, excess penetrant removal, developer application, inspection and evaluation. Let's go through each step in detail, because understanding this process is key to understanding how the method works. Step 1 is arguably the most critical: surface preparation. The test surface must be cleaned to remove any dirt, paint, oil, grease, or loose scale that could either keep penetrant out of a defect or cause irrelevant or false indications. Think about it: if there's oil or grease covering a crack, the penetrant can't get in. And if there's paint or rust on the surface, you might get false indications that look like defects but are actually just contamination. Cleaning methods may include solvents, alkaline cleaning steps, vapor degreasing, or media blasting. The choice depends on what kind of contamination you are dealing with. However, there's an important warning here. If media blasting is used, it may work over small discontinuities in the part, and an etching bath is recommended as a post-blasting treatment. This is because aggressive blasting can actually close up tiny cracks, defeating the whole purpose of the test. The goal of this step is to achieve a clean, dry surface where any defects present are open to the surface and free of contamination. Without proper cleaning, your entire test will be compromised. Professional inspectors often use lint-free cloths and make sure the surface is completely dry before moving to the next step. Step 2. Penetrant application. Once the surface is properly prepared, it's time to apply the penetrant. The penetrant may be applied to the test component by dipping, spraying, or brushing. For small parts, dipping the entire component into a tank of penetrant is efficient. For large structures like welds on pipelines or aircraft fuselages, spraying from aerosol cans is more practical. And for very localized inspections, brushing works perfectly fine. The key is to ensure complete coverage. Every square inch of the surface you want to inspect must be covered with penetrant. You can't inspect what you don't coat. Most inspection kits use aerosol spray cans because they're incredibly versatile. You can take them up ladders, inside confined spaces, and into difficult-to-reach areas. The penetrant itself is specially formulated to have very low surface tension, which allows it to flow easily into even the tiniest openings. It's this property that makes the whole method work. Step 3 is where patience becomes a virtue: dwell time. The penetrant is allowed dwell time to soak into any flaws, generally 5 to 30 minutes. This is the waiting period where the magic happens. During this time, capillary action draws the penetrant deep into any cracks, pores, or other surface defects. The longer the dwell time, the deeper the penetrant can penetrate. But how long should you wait? That depends on several factors. The type of penetrant you are using, the material being tested, the temperature of the environment, the size and type of defects you are looking for. For general inspections, 10 to 15 minutes is typical. For very fine cracks or cold temperatures, you might need 30 minutes or more. It's crucial not to rush this step. If you remove the excess penetrant too soon, you won't get adequate penetration into defects, and you'll miss indications. However, you also don't want to wait too long, as the penetrant on the surface could dry out. Most standards and procedures specify exact dwell times that must be followed for that specific application. Step 4. Excess penetrant removal. After the dwell time is complete, we need to remove all the excess penetrant from the surface while leaving the penetrant that has seeped into defects alone. This is a delicate balance. There are 3 main removal methods: water washable. Some penetrants are formulated to be washed away with plain water. These are convenient but require care not to overwash. Post-emulsifiable. These penetrants require a separate emulsifier chemical to be applied first, which makes them water washable. This gives more control over the removal process. Solvent removable. The dye penetrant solvent removable method is most popular because it is low cost and very versatile. You use a clean cloth lightly dampened with solvent to wipe away excess penetrant. The key technique for solvent removal is to use a clean cloth for each wipe. You are not trying to scrub the surface clean, you're gently removing the excess while leaving the penetrant in the cracks undisturbed. If you are too aggressive, you'll pull penetrant out of the defects. If you're not thorough enough, the background will be too red, and you won't see indications clearly. This step requires skill and experience. It's one of the main reasons why proper training is essential for conducting reliable dye penetrant tests. Step 5. Developer application. After rinsing the penetrant off, the developer is applied to the part to be tested, which brings any penetrant that may have penetrated into flaws back to the surface. The developer is typically a white, chalk-like substance that creates a contrasting background. It serves two purposes. First, it creates a white background that makes the red or fluorescent penetrant highly visible. Second, and more importantly, it acts like a blotting paper. It draws the penetrant out of cracks through reverse capillary action, spreading it on the surface and magnifying the indication so it's easier to see. Developers come in several forms: dry powder, water-soluble, water-suspendable, non-aqueous, solvent-based. The most common for the spray can method is non-aqueous developer, which comes in an aerosol can and applies a uniform white coating to the surface. The developer, whether dry or wet, should be applied as soon as possible after the removal of the penetrant. Vote NDT GmbH. Apply it in light, even coats, building up a thin white layer. Too much developer can mask small indications. Too little won't provide adequate contrast. After application, you need to allow development time for the penetrant to bleed out of defects into the developer layer. Step 6. Inspection and evaluation. This is the moment of truth where defects become visible. The time of developer exposure can vary greatly, as larger damage is usually visible sooner and smaller cracks become visible much later, typically taking between 20 and 45 minutes. For visible dye penetrants, you inspect under good white light. The standard requires at least 100-foot candles of light intensity on the surface. Inspectors often use light meters to verify this. What you're looking for are bright red indications bleeding through the white developer. These appear as lines for cracks or dots for pores and pits. For fluorescent penetrants, inspection is performed in a darkened area with high-intensity OV black light. The defects glow brilliantly yellow-green against the dark background, making even the tiniest cracks visible. Not all indications are defects though. Inspectors must evaluate each indication to determine, is it relevant? Not just surface roughness or contamination, is it linear or rounded? What is its size and location? Does it exceed acceptance criteria? Documentation is critical. Inspectors record the type, location, and size of each relevant indication. Photographs are often taken for records. Rejectable indications must be reported, and the component may need repair or replacement depending on the application code or standard being followed. Now that we understand how the process works, let's talk about why dye penetrant testing is so popular. What are its advantages? 1. Versatility. It can be applied to a wide range of materials, including metals, plastics, ceramics, and composites. 2. High sensitivity. It is highly sensitive and capable of detecting minimal surface defects that would be invisible to the naked eye. 3. Cost-effective. It is economical, versatile, and requires minimal training when compared to other NDE methods. A complete kit can cost less than $50. 4. Portability. The aerosol spray can method is incredibly portable. You can take it anywhere up ladders, inside boilers, into tight spaces, or out to remote field locations. 5. Quick results. The results are immediate and visible. You don't need complex computer analysis or specialized interpretation skills for basic inspections. 6. Works on complex geometries. Unlike some NDT methods, penetrant testing works on parts with complex shapes, threads, corners, and irregular surfaces. 7. Non-magnetic materials. It works on non-magnetic materials where magnetic particle inspection cannot be used, such as aluminum, titanium, stainless steel, and plastics. These advantages make DPT one of the most widely used NDT methods in industries worldwide. Of course, no testing method is perfect. Dye penetrant testing has important limitations you need to be aware of. 8. Surface defects only. It can only detect surface breaking defects. Internal defects are beyond its scope. If a crack doesn't reach the surface, penetrant testing won't find it. 2. Non-porous materials only. Porous materials can't be inspected with dye penetrants because the penetrant will seep into the entire material structure, not just the defects. 10. Surface preparation required. Proper surface cleaning is essential for accurate results, as contaminants can interfere with the penetrant's ability to enter floors. This can be time-consuming. 4. Environmental and health concerns. Some penetrants and developers may pose health and environmental risks, and safety precautions should be taken when handling these chemicals. 5. Direct access needed. Direct access to the material is needed, which can be difficult in some situations. 6. Operator skill dependent. While the method is simple, accuracy depends on the skill and experience of the inspector. Poor technique can lead to missed defects or false indications. 7. Cannot be used on certain surfaces. Very rough surfaces can trap penetrant and give false indications. The method works best on relatively smooth surfaces. Understanding these limitations helps you know when to use DPT and when other NDT methods might be more appropriate. Where is dye penetrant testing used in the real world? Let's explore some common applications. Aerospace industry. This is perhaps the most critical application. Aircraft components like turbine blades, landing gear, engine mounts, and airframe structures are regularly inspected with DPT. The consequences of a missed crack could be catastrophic. Automotive industry. Engine blocks, crankshafts, connecting rods, wheel hubs, and chassis components are inspected during manufacturing and in service. Power generation. Turbine blades, pressure vessels, boiler tubes, and welds in nuclear, fossil fuel, and renewable energy plants. Welding inspection. Welds are the most common item inspected using liquid penetrant examination. This applies across all industries: pipelines, ships, pressure vessels, structural steel, and more. Manufacturing quality control. Castings, forgings, machined parts, and assembled components are checked before they leave the factory. Maintenance and repair. In-service inspections for fatigue cracks, corrosion damage, and wear patterns on critical components. Petrochemical industry. Pipeline welds, storage tanks, refinery equipment, and pressure vessels. From the smallest medical implant to massive bridge structures, if it has a surface that could crack, dye penetrant testing is probably being used to inspect it. Let's do a quick comparison between fluorescent and visible dye penetrants to help you understand when each is used. Visible, red dye penetrants, used in normal lighting. Lower cost, less sensitive but adequate for most applications. Easier to use, no darkroom needed. Perfect for routine inspections and less critical components. The red on white contrast is easy to see. Fluorescent penetrants, used with UV black light in darkened areas. Higher cost. More sensitive, can detect smaller defects. Requires UV light equipment and dark environment. Used for critical applications like aerospace. The yellow-green fluorescence is extremely visible against dark backgrounds. Better for rough surfaces. The choice between them depends on the criticality of the application, the inspection environment, budget constraints, and the acceptance standards you're working to. Many inspection shops keep both types on hand and choose based on the specific job requirements. Before we wrap up, let's talk about safety and best practices. Personal protection. Always wear appropriate gloves when handling penetrants and developers. Use safety glasses to protect your eyes. Work in well-ventilated areas. Some chemicals produce fumes. Avoid skin contact and never ingest these materials. Environmental considerations. Properly dispose of used materials according to local regulations. Many penetrants contain chemicals that require special disposal. Don't pour them down drains or into the environment. Best practices for accurate testing. Follow written procedures for code work. Maintain proper temperatures, typically 40 to 125 degrees Fahrenheit. Use calibrated timing for dwell and development periods. Verify adequate lighting with a light meter. Keep detailed records and documentation. Use quality control test panels to verify penetrant performance. Never skip the cleaning step. Store penetrants properly, don't let them freeze or overheat. Training and certification. For code work and critical applications, inspectors must be trained and certified according to standards like ASNTS NTTC 1A or ISO 9712. Following these practices ensures both safety and reliable results. And there you have it, a complete guide to dye penetrant testing. We've covered what it is, how it works, the 6-step process, its advantages and limitations, and where it's used in the real world. This simple yet incredibly effective method has been protecting lives and preventing failures for over a century. From the wings of the aircraft you fly in to the pipes that carry your water, from the cars you drive to the bridges you cross, dye penetrant testing is working behind the scenes to ensure everything is safe and reliable. The beauty of this method is that while the basic principle is simple: apply dye, let it soak in, remove excess, apply developer, and look for indications, the applications are incredibly sophisticated and critical to modern industry. If you are interested in pursuing a career in non-destructive testing, dye penetrant inspection is an excellent place to start. It's accessible, widely used, and provides a foundation for understanding other NDT methods. If you found this video helpful, please give it a thumbs up and subscribe to the channel for more content on engineering, testing methods, and quality control. Have questions about dye penetrant testing? Drop them in the comments below, and I'll do my best to answer them. Thanks for watching, and I'll see you in the next video.